There are multiple ways to determine if there are outliers in a data set. This video explores 3 different ways to calculate outliers. The data set that we will be using here is a measure of social anxiety for a group of 166 students. A number of the calculations have already been prepared in advance, and graphs have been prepared to help better understand these techniques. One of the 2 more conventional approaches is to calculate the standardized score, also known as the Z-score, for the extreme values in a data set. This requires knowing the mean and the standard deviation of the data set. With these values, you subtract the mean from your given value and then divide that difference by the standard deviation to obtain the Z-score. The conventional rule is that anything above a Z-score of positive 2 or below a Z-score of negative 2 would be considered an outlier. Furthermore, anything above a Z-score of positive 3 or below a Z-score of negative 3 would be called an extreme outlier. That allows us to further classify the Z-scores between positive 2 and positive 3 or between negative 2 and negative 3 as mild outliers. As can be seen here, the values are in column C. The values have been ranked from the minimum to the maximum. The common notation when you've ranked data is to list it as X sub parenthesis 1, X sub parenthesis 2, etc., all the way up to the maximum value. In this case, the minimum value is 5.4. The Z-score for that value is negative 3.37, which would be classified as an extreme score. The next 2 raw scores are 20.7, 25.3. These have Z-scores of negative 2.37 and negative 2.07 when rounded. Because both of those don't meet the negative 3 boundary, they would be considered mild outliers. Now the next value, the 4th value in the data set, is 26.4, which has a negative 1.995 Z-score, which doesn't meet the boundary of the negative 2 and would not be considered an outlier. Going all the way up to the maximum value of 99.9, it has a Z-score of 2.83, which would be considered a mild value, whereas 83, the next smallest value below the the maximum, has a Z-score of 1.72 and would not be considered an outlier. Graphically, this can be seen with this slide. The actual distribution of scores is indicated by the bars and has been approximated by a light purple normal distribution curve. The mean has been indicated, and each bar indicates further going out another Z-score. Anything beyond 2 Z-scores, be it below negative 2 or above positive 2, would be considered an outlier. That gives us the maximum value and 3 values. If you notice, the 4th value is very, very close. It appears to be on the line, but in fact is actually just a little to the right of that line, so it is not actually included. Anything between the 2 farthest fences would be considered mild outliers. So we have 1 mild outlier at the top end of the distribution and 2 mild outliers at the bottom end of the distribution, and then the minimum value is an extreme outlier. The next strategy, still using Z-scores, is to specifically say that a percentage of the values, for example, the uppermost 1% and lowermost 1% of values in normal distribution would be considered outliers. From the empirical rule, that's about plus or minus 7/3 of a standard deviation. So a Z-score above 7/3 or below negative 7/3 would be considered an outlier. Under this criteria, the minimum and the next smallest value of 20.7 would be considered an outlier, and the maximum would be considered an outlier, but all the values in between would not be considered outliers. In this case, there's one fixed value at which everything above or below the boundaries would be considered an outlier. Finally, the last approach is to calculate the interquartile range to determine outliers using this technique. This is more appropriate when you have non-normally distributed data, and this is found by obtaining Q1 and Q3, giving us the IQR, multiplying that by 1.5. We subtract that value from Q1 and add that value to Q3 to obtain the lower fence and the upper fence. We multiply the IQR by 3 and subtract it from Q1 and add it to Q3 to obtain the extreme lower fence and the extreme upper fence. In this case, the values end up being 6.4 for the lower fence and 105.6 for the upper fence. Looking at the graph for this, what we see is that the lower fence is here at 6.4, and the upper fence is at 105.6. Unfortunately, the data only ranges from 0 to 100, so both the upper fence and the extreme upper fence don't really apply to this data set, and for that matter, the extreme lower fence does not either. So we only have one value which falls outside of the lower fence, which is the minimum value, and that is indicated as the outlier in this box plot.